Hi everyone, welcome back. Today we want to continue our network security discussion, and we will also talk a little bit about privacy and continue to discuss Tor onion routing next class. Just a little recap. Last time we talked a little bit about internet history, web history, spent a lot of time on same origin policy, how do different domains send requests, and how would you determine whether a JavaScript can issue certain type of request. We finished off by talking about cross-site scripting and its prevention. The programming assignment just came out. It will be due in 2 weeks. Simon, our TA, will do a quick video guide demo / warm-up on Thursday, but please do start early. And last time we had a lot of students having problems with machines and in a very tight situation. Please do start early. Network security, lots of time you will see mentioning of this word reconnaissance. And it's just a scanning of network to see what services are up, what ports are open, what versions of software that server is running, whether or not certain firewall blocks certain type of traffic. This is a screenshot from the movie Matrix, the actual movie Matrix. And you see that Trinity is using nmap and doing some scan and trying to break into some city power system. So using existing vulnerability in SSH. So nmap is a network map. It's a free software. You can download it. You can play with it on Linux. Have it installed. And it's just to do this kind of reconnaissance. And there's also a GUI interface, nmap for nmap. You can download as well. And so it's a pretty easy to use, but you do have to be careful when you use it. There's a lot of legal issues. By the way, there's lots of other network scanning tools. The ZMAP is extremely efficient tool that scan network of a particular address space that you wanted to, and so runs pretty fast. There's a lot of legal issues, and this is, I would say, network scanning is still a gray area. There's no certain yes or certain no. Make sure you do get written authorization from the entity that you plan to initiate and scanning. Sometimes you see this as it's very difficult digital cyberspace versus physical space. See, if you walk around my neighborhood, I would not consider you as suspicious, although I'm very good at spotting cars that don't belong to our cul-de-sac. But then in the digital world, if you doing like port knocking, you're just scanning the ports from 1 to like 10,000. It does look very suspicious. What are you trying to do? A typical web server has port 80 open. That's the legitimate clients would normally connect to 80. And so do be careful. Be careful and then pay attention. And sometimes, I remember when I was in grad school taking networking class, and the instructor said that he was scanning some National Supercomputer Center's address space, and then got a phone call. So you don't want to be on a blacklist. Denial of service attack is something that we talked about before. If you run, like if you graduate from Virginia Tech, you run, or you'll help run a major global infrastructure, so like Amazon Web Services, you know, the first thing you want to do is to have backups, so have fault tolerance. And you see there's a lot of dispersion on Amazon servers, and so that local, you know, in Asian continent, they have their own local infrastructure. Amazon availability zones, these are the concept that Amazon EC2 came up in order to achieve fault tolerance, and they have different zones have complete autonomy, independence from each other. They run independent cooling, power, and network. And so if one zone goes down due to fire or flooding, you know, with the climate change, you never know. And so you have you know, it won't impact other zones. And for a lot of time, that denial service attack, the biggest prevention, the most effective prevention is to have more servers. And so I want to talk a little bit about some of all the attacks that you know that no longer work, but then the concept is useful in terms of understanding some of the issues involved in flooding attack. A lot of the denial of service attack is that the server cannot distinguish a legitimate connections from attack connections. So one of the attack is called SYN flood attack. SYN flood attack, the name came from the TCP handshake, where the client send a SYN request, the server send a SYN ACT response back, incrementing the client sequence number and also add its own sequence number Y in this example. The client, if wanting to continue the connection, would choose to increment the server's sequence number and send back a acknowledgement Y+1 with its own sequence number incremented X+1. And so this is, you know, if you ask, okay, Y+1, why not +10? Well, this is just a protocol. This is how people decided what to do. But then, you know, it is suffice that you know, both parties now gets confirmed that they do want to start a communication. The SYN flood attack is where the client, of course, is not a real client, is an attacker, and an attacker try to fool the server, and by keeping by sending a lot of half-open TCP connections, and so this is SYN. The client just send a SYN request, say hello, I want to connect, and then disappeared, and then the server is waiting for the client to get back because the server wanted to start transmitting data and therefore keeping X, keeping Y, and then, you know, client 1 has a set of sequence number, client 2 has another set, and all of these and together with the client's IP address, port number, take space, take memory space, and take buffer, and the server at some point will run out of space serving legitimate connections. And so this is would cause a DoS attack, denial of service attack. The possible way of blocking, and so you're right, can we just block IPs that sends too many SYN requests? So of course you can, right? But then the problem is that the attackers would not send everything from the same IP. They would use, you know, compromise the computers all around the world to send. And so you never get to see, you know, like when you get a spam calls, right? You block one call, there's another call with a different number. It's all made up. And so a simple prevention to SYN flood attack is to have timeout. And then timeout doesn't have to be a specific hard-coded number. It can change and can adapt. Another prevention is called SYN Cookies. SYN Cookie is an extremely elegant and simple idea. So recall that part of the problem is that the server needs to store client information. With SYN Cookie, the server doesn't have to store anything. The server just upon receiving the SYN request to increment the sequence number and send its own sequence number, and then forget about it. And so what in the previous design, you can't, the server cannot, because when the client sends back the SYN act packet, the server will have to validate, is this a legitimate request continuing the previous request, the protocol. If you completely drop everything, erase everything, how could you confirm that this is indeed a valid SYN act request? The beauty of SYN cookie is that the special sequence number that that is generated by the server is special. It's a function of the client information and then a secret, a special secret only server knows. And so only when the client follow the protocol, then the sequence number will check out. And in the meantime, no one else can forge this sequence number. And therefore, if the only way to pass the TCP handshake is to follow the legitimate sequence. And the server will be able to validate whether this is indeed the third leg of the TCP handshake or not. If the client try to skip a couple of steps, then it will be caught. And the hash function is used, and so it's a keyed hash. You hash with the source info, IP port, and destination info, the secret that only the server knows, and the counter. So some other some other network concepts and then and attack types. So one of them is related to this ICMP protocol. ICMP is not an attack. It's just a protocol. It's internet control message protocol. The most popular one is ping. If you want to say, you want to find out whether some server is up, and you say it's ping cs.vt.edu or cs.www.cs.edu. So this is the most popular one, but then it turns out that ICMP has other code. If you look at the type and the code, there's all kinds of functions that allow the system admin to examine the network status. One of the commands that I really like is called Traceroute, and Traceroute allow you to use UDP protocol to check out what are the routers that are on a path between point A and point B. And so you just send a whole bunch of requests, and then with a time to live, with a short time to live, so that would allow you to get a response from intermediate routers. And I just did Traceroute to a California server, and I didn't wait long enough. When you see this star, that means the routers does not participate in Traceroute. It's blocking Traceroute, so you cannot find out the IP address, in just for security purposes. Of course, the ICMP protocol could be leveraged to do some kind of attack. And before there's an attack called the ping of death, and it's very, very important to know this is different from the blue screen of death. And of course, this is also another old-fashioned blue screen of death, old-fashioned attack where Windows would just shut down, and before it crashed, it showed this ominous blue screen, and then and so in ping of death is where attackers send an oversized ping packet and just cause buffer overflow. Stopped working, it's already fixed. Ping flood attack, where attacker sends many ping requests to a victim, and so if your victim has a shorter, a narrow bandwidth, and attacker has a fast wide bandwidth, and then cause of flooding. Ping can also, there's also broadcast mode for ping, and so you just send one request, then everyone on the subnet will ping you back. And when attack is, attacker, instead of using its own IP address, you use a victim's IP address. Then all the ping responses are sent to the victim and causing flood. And this is also known as a Smurf attack. And so in general, that you don't want to have this type of unexpected surge of connections. Sometimes in rare events, and say post 9/11, there are a lot of flash crowds of visiting news websites. And so those are the legitimate requests. IoT devices now was reported to generate a huge amount of spam messages. And some DoS attack have actual humans launching the attack unintentionally. Say if you post a URL, the victim's URL, which has a very narrow bandwidth, and you post that victim's URL on a very popular Facebook page, or Twitter, and then that URL gets visited by a huge amount of people and causing flood. And so if you run a server, the biggest concern that you have is availability. Anything that would cause would contribute to having more robust availability, you should go for it. And security is part of that. Availability property is part of the security. So don't think that, oh, I'm working on availability, this is not security, I should really work on security. No, availability is security. And so we want to spend most of the time on TLS. And also I want you to know that my job in this course, if you ask me what do you think is the most important thing that we should learn, and I would say TLS. Understanding how TLS work, of course, require you to understand how public key crypto system work, certificate, public key infrastructure. But TLS is the most important component in modern day cybersecurity. So make sure that you understand why it's necessary, how it works, and why anything else would not work. And this is all related to network transmission security. And for the threat model, we assume you have an attacker who intercept, modify, delete, and impersonate. And so I want to go through a couple of exercises just to warm up yourself and give you more motivations to appreciate TLS. And TLS, of course, is a bit complicated, and then you may wonder, okay, can they do something easier? The answer, of course, is no, but let's try. Alice wants to authenticate herself to Bob. Maybe just say, I am Alice, and use Alice's the IP address. But this clearly would not work because anyone intercepting this can replay and impersonate Alice. Sending Alice's password over as a proof would also be insecure, and because that information can be intercepted by other people as well. And so replay attacks are still valid in this simple, let's call it AP 3.0, Authentication Protocol 3.0. Okay, how about we encrypt Alice's password? And Eve, we know, does not have the decryption key, and say only Bob has it. So Eve cannot decrypt will this work? In what scenario this will fail? Oh, well, this doesn't change anything at all, really. If the encryption is deterministic, meaning that the same password gets encrypted every time it's into the same ciphertext, then you can intercept it and then just replace the ciphertext. The ciphertext become the new password. And so the next attempt, let's call it AP.4.0, we said that, okay, we really want to prevent replay attack. And so how about we introduce this nonce, which is just a random number which very rarely would repeat itself, cannot be predicted. What's the next random number? And the nonce is generated by Bob as a challenge. And so Alice say, hey, Bob, I'm Alex. And Bob says, I want to challenge you with this random nonce R. If you can encrypt it with our shared key. And so I should say this is assuming that Bob and Alice has a shared key, KAB. Then Alice would send the nonce, will encrypt it live in fresh nonce encrypted with the symmetric key freshly, and send the ciphertext to Bob. And Bob, once received this ciphertext, would decrypt using the shared key and then just make sure that it's the same nonce. This is a liveliness check and making sure that there's no replay. So meaning that if Eve intercepted today's communication and try to use it tomorrow, she will fail because tomorrow it will be a new nonce, R prime. So this is in general a good way of preventing replay attack. Okay, having nonce, having this challenge. Some people call it challenge nonce. Well, it does prevent replay attack, but then using shared key, we said is just it doesn't work on the internet, right? So how about we use a public key setup? So say Alice has a pair of public and private key, and tell Bob, hey, I'm Alice. Bob send back the nonce, assuming Bob knows Alice's public key. And then Alice would encrypt nonce with her private key, which of course only Alice knows. And Bob, using the private key, using the public key of Alice to decrypt and making sure it goes back to the same nonce. But then, however, this AP 5.0 has a step that where if Bob does not know Alice's public key, and then Bob will say, hey, tell me what your public key is. and Alice sends back KA+. And that is very disturbing. Is this secure? This is only have 1, 2, 3, 4, 5 steps. What is the most problematic step? You should all at this point say, oh, Alice shouldn't send her public keys. Bob shouldn't just accept the public key. Should demand something else. What if that public key got intercepted by Eve and Eve insert her own public key, like in all the man-in-the-middle attacks that we talked about. So let's see, indeed, that AP 5.0 is vulnerable to man-in-the-middle attack because anyone can intercept all these communications, right? Intercept nonce. And next step is where Eve, instead of relaying Alice's encryption of nonce, Eve encrypted nonce using her own private key, right? Anyone can generate private key and public key pair. So Bob, having no idea what is the correct public key, would ask, okay, please send me your public key. And at this point, that public key of Alice, of course, was dropped by Eve and instead feeds Bob with Eve's public key, KE+. And Bob, having no idea that this is the wrong public key, would use it to verify the encrypted nonce, and then it checked out, and then start to communicating using Eve's public key, which is the wrong key. Okay, and so then the result is that Eve will be able to play both sides and intercept all messages. Of course, she can also tamper with the messages. And so the root culprit, or one of the culprit, is the lack of knowledge of the right public key. And so we've been saying this again and again, and by this time you should, if you follow closely, be very proficient with this recognizing the man-in-the-middle attacks. And then the need to use the right public keys. And how to do it, just to use a public key certificate signed by a CA. Right, so this certificate binds the public key, which seemingly like a random strings, with a domain name, with the entity's name. Okay. And I think on today's internet, or many websites are start to use TLS 1.2, which started like 12 years ago. 1.3 started 2 years ago. But TLS, transport layer security, ensures CIA confidentiality, integrity, authenticity. And it's very important for you to remember that this is the only way. No cutting corners. There's just no cutting corners. And so HTTPS is where you run HTTP on top of TLS. Okay. So 3 phases. The next few slides are the most important slides of this course. And of course you shouldn't. We see in some aspect of it before. How does TLS work? And a lot of people don't know how TLS work. And so you should feel very proud after this lecture. 3 steps. First step is handshake, similar to TCP handshake, but then with more information. And then key derivation, and then just the data transfer. In the handshake, of course, is the most important step in TLS. You have a client send a request to server requesting to connect, and it's always a client sending the request. So you have the TCP regular handshake, and then we have this SSL hello, and this probably should be called TLS hello. TLS hello, and then the server sends the certificate, and then of course you have no idea this is happening because your browser is handling this, and so the browser download the certificate which contain the public key of the server, and the browser verifies the certificate against the CA's public key. Okay, and we talked about the digital public key, digital signature scheme, and this means that the verification is you double check the signature, making sure it is indeed a signature of the statement, the hash of the statement. So you have to compute the hash of the statement as well. And that if the certificate check out, then we are in business. So, and the rest of it is just a simple, I would say straightforward, because now the client will pick a master secret, MS, and encrypt the MS using the server's public key. In server, having the corresponding private key will decrypt and get MS. And now we're in business because they have the shared secret key, and then they use this to derive additional keys. And then for TLS, we have different direction using different encryption key. Because subsynchronous encryption are all based on symmetric encryption. So, one direction is one key, the other direction is a different key, and there's also message authentication code key, MAC key, for message integrity, and then recall that this is just a keyed hash, and that's a different key from encryption. And so once that all the keys are done, the data transfer is just using all these elements together. You have you compute the message authentication code and to make sure that the message, if the message gets tampered with, you'll be able to detect it, and concatenate with the key hash with the original payload, and then encrypt the whole thing with the encryption key with some header and send it over. And then the receiving end will be able to decrypt because they share the same key. So that's it. That's the TLS. That's the TLS. And then, you know, CIA properties. It doesn't guarantee availability, but make sure that you understand how TLS work. And it's if you think about it, it's pretty amazing because you have the client who the server doesn't know the client, right? When you surf on over stock.com, the server knows nothing about you. And then you establish a communication channel with a shared secret, and then you will be able to encrypt messages back and forth using shared secret and on the internet. And this is very, very powerful, very, very amazing technology. So we just said this before. And before we end, I want to start some discussion on Tor onion routing and just the privacy. And next class, I want to say a little bit more. And then for next week, we want to talk a little bit more on the traditional network security like DNS security, session hijacking, and so on. But I feel like Tor onion routing is just a fun topic, and you already have all the knowledge about crypto, so you should be able to understand. But so just in general, privacy is something that you do want to protect. PleaseRobMe.com is a website to raise awareness about our sharing. It used to be to get the information from Foursquares, which is a location-based social network. When you can check, you can say, oh, I check in at South Main Kroger or University Mall, Starbucks, and then people know that you're not at home. And so someone set up a website and just list all these names, and then in their information that they are not at home. Location, knowing where you are, and there are news that people triangulate, just track location in stalking, cyber stalking, and then physical stalking as well. Triangulation is where satellites use to locate someone. For in 2D space, you have you need 3 satellites to find out where you are. If you consider flying the altitude, then you altitude, then you need another satellite, the 4th satellite. Back in 2006, AOL, with just really good intention, decided to share a lot of user searches, and then since then nobody was there, nobody dare to share user data because AOL got so much heat. And people find out the data is not properly sanitized, and you can still link the search records of the same person. And so I remember there are people who search like a diapers and and then how to kill your wife. It's just a very weird searches, a combination of searches as well. Bundled spyware, Kazai is a P2P file sharing app, was extremely popular maybe 20 years ago when peer-to-peer file sharing first came out, maybe 15 years ago. When I was in grad school, it was very popular. it turns out it also has bundled software that use your computer free cycles, but somehow in this alternate, this bundled software overshares in the tax return of users got published. So extremely scary, and so it's you want to know that when you download something, it does what it's supposed to do and nothing more. Web surfing, of course, you don't have a lot of anonymity when you surf because your IP address is your ID, and anonymous surfing is this sort of the ideal scenario where if no one knows who you are and what is your IP address. But then it is a oxymoron in the sense that you have to get responses from servers. Server need to know where to find you, right? Need to know your IP address in order to send you the content. And so if you are hiding, like if you don't have a home, how can you order Amazon packages, right? So a lot of time, and a lot of time that you have routers, so who may be eavesdropping, and it may be compromised, and people eavesdrop at the routers and be able to intercept traffics. A lot of time that you know when you read the cyber attack news, it often mention the difficulty of pinpointing the location of the attacker. One of the most popular attack software used in hiding address is VPN. VPN is where you just have a proxy, use a proxy server. And so you connect to a proxy first, and then proxy will generate IP addresses. And assuming proxy is not cooperating with the government, with the authority, then your IP address is fine. And of course, there's different level of virtual channels you can think of. In a lot of times that this change of IP address, so think of this as a special tunnel. And you can tunneling at different levels of the network stack, and then different types of packages. So and to some extent that when you see some package, when you intercept some network traffic, and then you say, oh, this looks like DNS traffic. You may be wrong. It may look like a DNS packet, but then it's actually like HTTP packet. As long as as long as the receiving end will be able to interpret this traffic and peel off the outer layer, then the inside the payload may be something else. And so this is in general called tunneling. And if you look at the onion routing tool, onion routing is essentially similar concept. Similar concept is used, and then together with the other type of like mixing and so on. So here is an example of the tunneling. You have SMTP traffic, but then the organization firewall may not allow SMTP traffic, but does allow HTTP traffic. Then you can put the HTTP header. You break the SMTP into smaller pieces and then put it into HTTP traffic as payload. Okay, and then once the receiving end receives it, will peel off the superficial HTTP layer and then get the actual payload. SMTP is a mail transfer protocol, is for email, right? And then it doesn't have to be SMTP, it could be other traffic, proprietary protocol. Okay, and anything. HTTP, of course, is the most permitted type of traffic, and then so packaging whatever in for example, like chat messages, IRC, the chat messages under HTTP, then you can fool firewall. Doesn't have to be at that level, application layer level. It can be other different layer. Data link layer has this PPTP, usually runs in Windows. So because of the network, the design allow this kind of encapsulation. So tunneling is possible. How to trust? When we talk about VPN, anonymous surfing, you still have to trust the VPN server not giving away your IP address, right? Is there any way that we can do better anonymity? We don't have to trust a single server. So a lot of people have looked into this, and the most commercial successful technology is called Tor onion routing. And the basic idea of all these anonymity is to hide your traffic among the crowd. If you just do your own traffic in and out, and people will be able to see, oh, I intercept this traffic, and then this subnet, there's only like a handful of people, this must be one of hers. But if you hide this, if it's you encrypt everything, you hide this among all the other traffics, and then also you don't directly go to your destination. You send your traffic halfway around the world before it reaches the destination. Like if you know that you were stalked by someone, you don't drive back home immediately. You drive around some other places to lose the tail. And so similar deal. Okay. In some lots of traffic, you mix packages, and also you don't directly go to destination. You cause confusion, okay, in the traffic route, and you hide yourself. And this is onion routing is now the first attempts in the mixed network invented by David Chang back in the 80s. It described the concept, what Alice need to do in order to send Bob this type of anonymous, send Bob a message, but don't want other people who monitor the traffic be able to find out who sent what to whom. Okay, so now cannot find out. Say Eve is monitoring the one machine. If Eve monitor the whole internet, correct all the routers, of course you will be able to be able to have a better guess. But then if Eve just have access to a small number of machines, what Eve would be able to see is just some encrypted traffic going in and encrypted traffic going out. And then this traffic, but then it has to reach Bob, right? It has to eventually reach Bob. So Alice would just send this message first to someone somewhere else, put it into an envelope, and another envelope, and once the next hop proxy gets the envelope, we'll just peel it up and then see another envelope, but then say, oh, route this to the next hop. And so at each hop, everyone will just route some messages, and they don't know it's originally come from Alice, or Alice is routing this for somebody else. And so all they do is I route some messages, some comes in, some goes out, and then the last hop will send the message, encrypted message to Bob. But then the last hop still doesn't know, is this the final destination to Bob, or Bob is, or that is the message is supposed to just go through Bob. And so if we just have Al is doing this and nobody else does this, of course this does not work. What this mixed net should depends on is everybody does this. Everybody would put the message, encrypted message into these kind of envelopes, and then start routing. And then of course it takes more overhead, it's slower, but then with enough this traffic, it's very hard to pinpoint who is sending what to where. And so this is the basic concept of mixed net, and also in onion routing, and then just in general all these anonymous routing techniques. And of course it's gonna be slow, and we assume the proxies follow the protocol. They would not say, oh, I dropped all the messages. So we assume that all the proxies, we trust them following the protocol, they will relay it. But it's semi-honest. They may attempt to peek into and peek under the envelope and try to understand what is a message, who is sending, who is the receiver, but they won't be able to find it. The mixed network, the original proposal is use a public key crypto system, of course, extremely slow. But then if it's for email, it's not time sensitive, it's still okay. Next class, I want to say more about the onion routing and also the hidden service. And this is where services such like WikiLeaks website uses, where you cannot find the actual location of the server, but still be able to visit it and get post information, get information, and so on. So next class, on Thursday, we'll have some demos coming up, one related to public key infrastructure, the other related to our programming assignment. Do take a look at the programming assignment. And I think that's it for today. Thank you so much. Bye.